different ways to accomplish this, but the whole thing is about the efficiency. First, are we all aware of the meaning of the word algorithm? What is it? How would you describe an algorithm?
Set of instructions.
Okay.
Go from an input to an output.
Okay, there are many things that do that. Can we get a more precise definition? First, number one is automatic procedure. So you cannot just come up with some idea. So you have to have clearly instructions. So it has to be automatic. And you cannot adjust it. So it's a procedure that doesn't change from one number to another. You just, ahead of time, report the procedure that you will use and whatever inputs are being used. So it's automatic procedure. What else? For what? Usually we say in mathematics for calculating something. You also have algorithms how to improve, I don't know, garbage collection in San Diego or something like that, but that's not what we are interested here. We are usually interested in algorithm where you calculate something. And it's very important whenever you write a list of instructions that list of instruction is finite. So you cannot have infinite list of instruction because program cannot read through infinite list. So it's a finite list of instruction or finite automatic procedure for calculation of objects. And that's what this one is. But we have many different procedures because this is a very easy task to find the greatest common divisor. What can we do, for example? But it'll take forever for big numbers. Can I write all the prime factors of 4131, yes or no? And then build all the factors of 4131. So have a list of factors of 4131. Have a list of factors of 2431. Then compare the lists and find the common elements that appear in both lists. Do you agree? And at the end, find what? The greatest among them, and that's it. So this is abstractly, this is a good procedure, but what? It'll take forever. Next one is, can you do a better procedure?
One I think of is just find the one that's the smallest divisor.
The smallest, but from smallest one?
Wouldn't you have from the smallest you'd have the greatest, wouldn't you?
Not really.
Okay.
No. If you get the smallest, the best thing you can do is to divide both of them and make them smaller and go that way. That's one of the ways. And then the procedure that people would often report is, and that's how you do this very often in your algebraic classes, factor both of them and then see whatever they have in common at the highest possible power. Is that how you can do it? That sounds like a good procedure, but it's too expensive. Why is it expensive? Because factoring is a very complicated procedure, and then you might get stuck or it takes forever to finish factoring. So that's, again, inefficient procedure, and you will see how Euclidean algorithm actually gives you a very quick and easy procedure to find greatest common divisor. And I'll show you first what do you do, and then later on we'll explain why is it really doing what we said that is doing. So here it is. So here's how procedurally that all goes. There is one little detail when you have to make it sure that you keep track of the rows of the numbers that you get. We'll just keep applying division algorithm, quotient remainder theorem. So we'll take 4131, and I'll put it in a box. You will see why. Because that's an important number. It's a number that stays in the procedure. And here is 2431. When you divide 4131 by 2431, what is the quotient? 1, so that's your quotient, and there is a remainder. And that remainder I also put in the box. And how much is that remainder? 1700. Think of this matrix-wise as a position 1, position 2, and position 3. What happens on the next line? This guy stops participating. Position 2 takes position 1. Position 3 gets into position 2, and then you divide again. So what would that be? Who's now here? 2431. Who is here now? 1700. What is the quotient? Is it 1 again?
Yes.
It doesn't just happen. So 1 is, so what's the remainder?
731.
731. What do we do now? Again, disregard that outside number, remove this one, let these two guys slide. So it's 1700 equals 731. This time quotient is what? 2. So this is what? 1462. So remainder is 238. And then we keep going. How long? We'll see. First, will this ever stop?
Yeah.
Why? Because these numbers here are always smaller and smaller by quotient remainder algorithm. So generally, I cannot keep getting positive numbers. I cannot get negative numbers. So at a certain point, I have to get which remainder? 0. Because if I don't get 0, I'll just keep dividing. If I get 0, then I'll stop. And let's see. So it has to stop in finitely many steps. So it is an algorithm. So who's here now? 731. Here is 238. I think 3 times now. And 3 times, this is this 714? 24, 690, 714, so the remainder is 17. And then we get 238. Here is 17. What would that be? What's it? 14. So that's 170 and 68, 238, and remainder 0. The moment when you get remainder 0, you stop. And who do you read? You don't read, usually we say the following, don't read this line, but read maybe the last non-zero remainder. Who is that? 17. So go to the previous line and read that number. That's your GCD. That last non-zero remainder is GCD of 4131 and 2431. And then in the notes, you can find the procedure, how you can also organize a program to do that, when you kind of store the results and then you keep going and you do the next instruction. And you run through the counters until you reach that remainder 0. So this is the procedure. Any questions how to apply the procedure? And that's what I usually ask. I want to make sure that everybody can do the procedure. My question is, actually, there are a couple of things to see here. And I want maybe to argue on this numerical example, and hopefully it will explain why is it working in general case. I always tell you that's one of the main things I would like to see on Monday. I would like to see when I ask you a universal statement and you give me an example. And that's what I'm doing right now. So I want to show you that Euclidean algorithm always works. So I'm not proving it. I'm doing what? I'm illustrating it. So sometimes we see things better. So I'm not pretending that this is proof, but here it is. My question is, first question is, how do I know that 17 is divisor at all? Do I know that or I don't? Let's see. Does 17 divides 238? Is that evident? Yes or no?
Yes.
From which line?
Second
Last
last.
line. 17 is a factor of 238. But now let's go to the line before. Is 17 a factor of 17? It's itself. Is it factor of 238?
Yes.
So is it factor of both of them? Can I factor it out on the right side? So it must be a factor of what? 731. So if I call this line number 1, line number 2, line number 3, line number 4, line number 5, I can say 70, C, line number 5. 17 divides what? Itself, and 17 divides 238, then 17 must divide what? 731, C, line number 4. And now what do I do with line number 3? Who do I need in line number 3? Now I know what 17 divides 238, but I just obtained that 17 divides also what? What did I get now? 731, so it must divide what? Look, who do they build on the next line? In 238 and 731 on line number 3, 17 divides 1700. So can I keep going higher and higher? And at the end, I will get that 17 divides what? After a couple of steps, it will divide 24031 and 1700, so it will divide what? 4131. I can actually write, so this was line number 3. Line number 2 says 17 divides 731, and 17 divides 1700 implies 17 divides 2431. That's line number 2. And line number 1 says if you divide 1700 and you divide 2431, you must divide 4131. So what did we kind of illustrate? And that could be done in any case. You go line by line and you catch next in the... So you can think of these numbers as being the whole line of numbers that are kind of younger and younger in the procedure, like first the oldest ones, and then you are getting younger and younger numbers and that are lower in rank. And then, but when you do the argument, you go from the bottom, from the last products until you get back to the original numbers. So it is, yes.
Is there a procedure for three numbers getting the GCD?
Yes, you do 2, and then when you get GCD, then that GCD, and it's very often in mathematics. When you have more than 2, you just keep repeating the procedure. All right, yes.
If they're both prime numbers, does this method work?
Yeah, you will get 1.
You will
Yeah.
get 1?
Yeah, let me show you. Let me show you. First, let me finish arguing on this example. What else? What did I show or illustrate, not prove, but illustrate in this case that the number that you get at the end is a common divisor of both of them, do you agree? But why is it the greatest common divisor? You use the same argument, but not from the bottom top, from top to the bottom. And you say the following. Why is this the greatest one? Let D be any other common divisor of 4131 and 2431. So now what? If that D divides both this and this, both this and this, what does it need to divide? If that D is common divisor, it must divide this, it must divide this, so it has to divide what? This remainder. Now you go to the next line, I got these 2, so it must divide this. So the same way I went up to show that it's a common divisor, for someone else I would go down. So D, because of line 1, D would need to divide 1700. And then because of line 2, now when you have 1700 and 2431, D would divide 731, and I would go down, down, until in certain case I would get that D divides what? 17. So if that D divides 17, who's bigger, D or 17? If you are a factor of 17, 17 is, so from here, D has to be less than or equal 17, and that's it. 17 is the greatest factor. So going up, you showed that it's common. Going down, that it's greatest. And as I said, when you look at my notes, it's written a little more abstract, like it looks more like abstract mathematics writing, but basically this is the idea. All right.
If you reach a prime number, can you just stop?
Actually you can, but how do you know it's prime? particularly in because you know 3, 7, and 11 for low numbers, but if you have huge numbers, you have no idea that it's prime. Yeah, that's how you might test, among the other things, primality or quality of a number. So, but I want to show you something else, and then I will answer that question about prime numbers. There is something that we'll use later on in chapter 6 somewhere, and that's one very important theorem. It's called, people call it very often Bézout's theorem, and it says the following. So this hopefully illustrates why this 17 really does what we said it does. But there is something else, and that is, can I write, question, sorry, can I write 17 as k times 4131 plus L times 2431? Where k and L are, of course, what? Integers. That sounds very unlikely. Look how huge it is. So for example, if we live in a country that uses the money that has so I have one bill of $4131, and the other bill is $2,431. Can I pay the amount of $17? But pay and get back. Some of them might be negative. So for example, I need to pay to give you $17. So what? I keep giving you $4,000, and then you give me back some $2,431. At the end, you are exactly on $17 paid. Could that be done or not? Yes. So here it is. Generally, the answer is yes, and that's that big theorem. In the language of linear, how many of you are taking linear algebra now? How many took it already? Not too many. All right. In the language of linear algebra, that would say the following. If you use those two like vectors as a base, can you represent this vector? Is it a linear combination of those two basis vectors? And the answer is yes. However surprising it is, we can pay off $17 this way. And sometimes they ask problems like this. If you want to measure 17 quarts of some liquid, and you have only dishes like this big, and then filling in, throwing away, can you do it? The answer is yes, and here's how. It's again using Euclidean algorithm. What do? Generally, it's fairly simple idea, but to carry it carefully, you have to be well organized. What are my boxes that showed up on the list? Who was there in the beginning? Who's the highest? 4131, do you agree? Who's the next in lower one is 2431. Who is the first product of this procedure? 1700. So that's third generation. Who's next one? 731. Who's next one? 238. Who's next one? 17. So I need to represent 17. So my goal is to trade lower products with higher products, one step at a time. So here it is. I need to represent 17 with the top of the list. Do you see that? I'll say the following, one step at a time. Who are the first two neighbors above 17? Who are they? Do you see them here? Is there an equation where I can do that and represent 17 using those two guys? Which one it is? Number 4. So number 4 tells me. But now, instead of calculating from here down, I go backwards. So I can say the following. And don't multiply out, please. Keep important numbers in the box. So 731 minus 3 times 238 equals what? 17. What is this telling you? If I live in the country, when the only bills are $7.31 and $2.38, I can pay you $17. Here it is. I give you $7.31, and you give me back $2.38. Agree? Good. Now what do I do? And here is that part that you need to memorize if you want this procedure. You cannot be too ambitious. You go by one step up. So here are the guys that I used. Now I go for one step up. So I still need to use which one? But who needs to be traded? 238 has to go. So now I want these two. So here it is. Keep 731. It's too early to get rid of that one. Keep that 3. But now is there a line where I can trade 238 for higher guys? Yes or no? Here's the line. So how do I trade 238? That line tells you, because 238 is at the end alone. So how much is 238? 1700 in the box minus 2 times 731 equals what? 17. What do I do now? Distribute, but never touch the boxes. Just distribute what's outside. So what do I get here? 731 minus 3 times 1700. And plus how many? Negative 3 times negative 2. That's okay. Outside of the box, you can multiply. So what do I get? Plus times 731 equals 17. So do I get 731? And 6 731s is what? 7 times 731 minus 3 times 1700 equals 17. So what happened here? Now I can pay $17 using only higher bills now, 1700, 731. You can check this. Just multiply out, subtract, you should get 17. So now how do I pay you with even bigger bills? I give you 7 of those, and you give me back 3 of those. Exactly $17 were paid. What's my next goal? Go by one more step. So these are gone. Now this is the actual one. So what should I do? I want these two. Who needs to get traded? Not both of them. Don't rush it. So who needs to be traded? 731, and here is the line. So I'll trade 731, so it will be 7 times 731 is traded as what? 2431 minus 1700 and minus 3 times 1700 equals to 17. So what is this? It says 7 times 2431 minus 7 times, don't multiply in, 7 of those big amounts minus 3 of those is how many? 10 minus 10 times 1700 equals 17. Once again, if you multiply out, you will really get the result. You should. I hope I didn't make, So what happens now? I'm almost on the top. I use these two. So who needs to be traded? 1700, and that's exactly one more line to trade it. So I'll say it like this. So when I trade it, I said the following: 7 times 2431. Do we have camera on? Good. Minus 10 times, what is 1700? 4131, last trade, minus 2431 equals to 17. Now if you distribute, what will that be? Not inside, just outside. Negative 10 times this minus will give me plus 10 of those, do you agree? And plus 7 will be what? 17 times what? 2431, and minus 10 times 4131 equals 17. So I'll give you 17 of those smaller bills. You give me back 10 of those bigger ones, and I exactly pay you $17.
So you have to be rich to buy cheap things.
No, it's just, what this says is that those numbers communicate well. That's what I would say, because they have low greatest common divisor, then they can really represent small things.
Seems like a good way to
Small.
keep tourists away.
To keep what?
To keep tourists away.
I see, okay. All right, good. What's left? So here is the main thing about Euclidean algorithm. So once again, first thing, you need to know how to execute it. Second one, to believe that it's really doing what it's doing. I didn't write you the formal proof. As I said, you can go through the notes to see it. But going from back on top, you can see that. And then probably the most useful thing is that procedure of Bézou's algorithm, where you actually you can represent that greatest common divisor as linear combination of two numbers. So those are the most important things, and nothing really different from there. Someone asked us, what happens if I'm dealing with two prime numbers? Then hopefully we should get what? One, but don't expect to get it quickly, because this procedure doesn't know that. This one just, measures their size, one comparing to the other. It doesn't see the factoring procedure. So even if it's prime, it must take 10, 15 steps until it sees the prime. So let's see what will happen. But as I said, since we have a proof, it must give us 1. So let's say what? 127. Is 127 prime?
Divisible by 3.
Oh, yes. We know all these algorithms. They were somewhere in the homework. Add up the digits if it's divisible by 3. But this one is 9, 10. It's not. It's not divisible by 5. By 7, it's not. Yes, because it's missing 13. Yeah.
Because that's near 12.
Then 11, no, because 1, 10, and 17, and that's it. So it is a prime. And then I want GCD of 127, and then one bigger number. But how do I know ad hoc if it's prime? Let's say 71, just to be on the safe side. So here it is. So these two numbers, actually, even one of them is prime, unless the second one is a multiple of it. But generally, but let's say, is that what you wanted? Both primes or one of them prime when you mention? Let's say the other one is not. Doesn't really matter. So 71, I multiply by 9, so I'll get 639. So that will not hurt either. So let's see what we'll get here. So 639 equals what? 127. Those are important numbers. And then, I was just lucky that they immediately reduce things. It doesn't happen always. So when you do 5 times, what do we get? 635. So suddenly, immediately, the first remainder was low. Let me go higher then. 662. Yeah, so that will make it a little, at least, but I hope it's not divisible. Yeah, so that will be bad. Doesn't matter. As long as this one is prime, everything is okay, because nothing can come out of it. Because this one doesn't allow any factor except itself, and 1. So let's see. So this is 5 times 127, so this is 635. When you subtract it, we get 27. So 27 is here. You see, I didn't get any spectacular numbers. 27 is here. So 5 is too much, so I have to go 4 times 27, which is what? 108 plus 19. And then 27 is 1 times 19 plus 8. Now 19 is 2 times 8 plus 3. 8 equals 2 times 3 plus 2. 3 equals 1 times 2 plus 1. 2 equals 2 times 1 plus 0. Who's your last non-zero remainder? And here it is. So what do I conclude? That they are relatively prime, and nothing else could happen because, as I said, this cannot allow any other factors, so that was all good. All right, so what makes this procedure so important is it is quite simple and quite quick. So you see, particularly, maybe not, even on this one. It would take me a while to factor out 662, and it would take me a while to see that 127 is prime. Here, I don't even know if it's prime or not. I just run down a couple of divisions, and you immediately get that GCD. So that's what's best about it, And as programmers, you need to think about it also. Not mathematicians just say, is there a proof or not? Or is there a construction or not? Programmers say, is there a construction that's efficient, that could be executed or implemented in a reasonable time? And that's why it's important. This could be implemented in a reasonable amount of time, very quickly, actually, even for huge numbers. Factorization for huge numbers cannot run quickly. Yes, Mary?
So you had two values that appeared prime, but they were very big, so you couldn't tell. And one of them wasn't, you didn't know. And you did this, and you got one at the end as your GCD. You'd know that at least one of them's prime, but
No.
you don't know for sure.
No, they might be
might
just,
have no-
yes, so like, like 3 times 5 is 15, and this one is 7, so 15 and 77. So if you run procedure for 15 and 77, you will get one
Comprised of entirely prime numbers.
of entirely different prime numbers, and that's it. So it just says that they don't share anything, but how are they constructed, you cannot conclude that. They just use different pools of primes, actually. Yeah. But, so what you did the converse of that statement. Statement was, if a number is prime, will I get 1? The answer is yes. If I get 1, does it mean 1 is prime? No, and that's what it is. P implies Q is true, but Q implies P is not. And that's what we showed with counterexample. So you see, you asked me, is this universal statement true? And I said, no, I gave a counterexample. We settled the issue.
Can you tell which one was prime?
No, not at all. They don't have to be. Yeah. All right. We kind of reversed the class. So we reviewed more in the beginning, and now we just covered the new session. So let me just, in these few minutes that are left, comment about the exam, and you know where to find exams and all that. I don't have exams. Just a second. No. Just a second. I will need a little time to pull out Blackboard then. Just to glance through it so that everybody sees where it is, and I don't want Yahoo. Here it is. $226. You go under content. I hope you already started to go there regularly. And then, so here are the practice tests. Exam 1. So let's say text only from spring 14. So, all right, so just looking at the old exams, of course, it doesn't give you the problems that we'll have on our exam, but it tells you roughly what to expect. How many problems? 10. Usually it goes half-half, propositional chapter 1 and chapter 2. So first one is just to show that you understand how to record things as propositional formulas. So it's just using P's and Q's, nothing fancy, no quantifiers or anything. If you understand contraposition, negation, and all that, so basic structure. Then what about the other one, showing that formulas are equivalent? What's the safest bet for that? Don't try anything fancy. Truth table is the safest bet. And then what about this one again? One of the applications to show if you can use the logic that we kind of learn or analyze to say and analyze statements from mathematics. Then here is 8-bit representation. Everybody remembers that? There was a quiz on that. For sure there will be something there. I didn't have any circuits here, but sometimes if they show up, sometimes they don't. Now we go to predicate calculus. In the beginning, I want you to show me that you understand the meaning of quantifiers. Sometimes you remember those systems, if they have solutions for every x, there exists y. First thing that you always ask is, are the variables free or bound? Look at this. There are two variables, x and y. Who's free, who's bound? X is bound, y is free. That means y you need to feed all the time, and x then I will run it through the whole domain. And here it is. I'm feeding 3, and I'm asking you now to run and tell me what happens. But what about this? Is it true for every s and every t that if they both have the property that they must be equal? So is there a uniqueness of such on P, on such Y, basically, and so on. And then, again, correctness of the argument here, the way we said it, contraposition and proof. Proof might be direct, might be contradiction, contraposition. Lately, we studied mostly contraposition and contradiction. Don't think that that's what I'll put on the exam all the time. Because it happens, we emphasize it so much, people come to the exam, every proof is contradiction, contraposition. Please don't. You know, if it's warranted, do it. If it's not, we always first want direct proof. That's our preference. And you say, would it be advantageous for me to do contraposition? And if you are benefiting, that's good. So if the product of two integers is an odd number, that both of them must be odd, is it good to do contraposition?
Yes.
Yes, because instead of concluding from the compound to elements, I would rather go from element to our compound. That's more natural flow, and that's what contraposition will do. What else? So here is the famous one. You saw that a million times. You see it appears on the exam on those. For these groups, so here I might do it for 3 or something like that, to have it a standalone statement to see if you can do the argument well. What else? Was it just 8 problems? Hope not. Prove that there are infinitely many prime numbers. Was that the theorem from the board? So generally that's, although this is online class, so they actually didn't really have the full board. Using Euclidean algorithm, find the GCD. Do we know how to do that?
Yes.
Generally just write those lines, nothing else. You know. What's it?
The explanation of why what your result is.
But not really. It's nice, you know. I want you to be aware of it. If I want it, I will ask you. If I said, using algorithm, find it. You found it, that's it. You called procedure from the book. You didn't give me something that you found somewhere else. So obviously it's a legal procedure. So you don't have to write it down, but if you want, that's fine. All right, see you on Monday then.
Are the solutions to the practice test online?
So solutions for the practice tests are online, so you can see them.